Goedenavond allemaal. Welcome everybody. Also our viewers online, a warm welcome to you. At this 1887th, now it's gone, it was in the top of the slide before, lecture of the Society. And it's the third lecture of this year where we celebrate our 225th anniversary. And this is going to be a very, very festive year, which we will start in January with an impressive lineup of movies, which actually have been initiated and selected by the speaker of this evening, Petra Rudolf. And it's my great pleasure to introduce you to her. Many of you know her quite well, I would say. She was a member of our board from 2004 till 2024. And after that, she was appointed honorary member. Well, as you can see from what I said earlier, she initiated this initiative with the Lustrum, but that's only one of her very many activities. And even though she is retired now, her commitment and energy are countless. It's amazing what you all did. So I have the difficult duty to introduce her impressive CV to you. And I had to make some selections, so sorry for that. But Petra went from Germany to Italy, actually, where she got her master's in Rome in 1987. And then she went to Belgium to get her PhD in, and now I need to check, 1995. And both were in physics and both were summa cum laude. So that already marks a very impressive start of a successful career. She came to Groningen as a professor in experimental solid-state physics in 2003 at the Zernike Institute of Advanced Materials, where she also served as the chair of the board. Well, she did many academic duties, and I will, please go and check out her CV online. But one of the, I think, impressive proofs of her academic citizenship is that she served as the director of the graduate studies overall of the University of Groningen from 2020. She got many awards, and well, I think the officer in the order or of the order of Orange Nassau is a very prestigious one, and it really shows how many things you accomplished during your career. And this was in 2013. What is not mentioned on her CV very extensively is her strong commitment to build the female academic society here in Groningen, but I would say worldwide. Petra really did a lot for the Rosalind Franklin community, for example. And upon her retirement, when we had the annual Rosalind Franklin dinners, we renamed this to the Petra Rudolf dinner. So we really hope that we can enjoy your wisdom and your mentorship for many more years to come. And as Jacqueline Skerpen, our Rector Magnificus, said yesterday, you really are the Nestor of the Rosalind Franklin Fellows. So that is something which I think we cannot applaud too often. Really. So let me see. Well, you really did a lot as an academic citizen. But next to that, and I would even wonder where you get the time, you were like a role model for the females, but also a model for, scientists. You had a very successful scientific career as well, with over 350 publications, awards, prestigious, and I think we are all very much looking forward to hear you talk about your hobby, the materials. Petra, the floor is yours.
Thank you. Thank you very much. I'm very happy to be here and to tell you something about quantum materials. I'm especially happy because this year we celebrate the International Year of Quantum Science and Quantum Technology. And I'm a little bit disappointed that in the Netherlands we did not celebrate that more. But at least we celebrate it tonight. Of course, there are many quantum phenomena, but I'm going to talk about quantum materials. And these are materials where the electrons do interesting quantum things. And we will hear a lot of different things they do. And they do these things when they feel tight in space. They also do these things when they behave as when you walk all alone early in the morning on the beach. The fact that there are billions of other human beings is not something that influences the way you move. Well, electrons in a normal wire, in a copper wire, they behave like this, and yet they have quantum properties. And then the most interesting, of course, are those electrons who very strongly feel the others, like when you are in a discotheque, and you know very well that when you have a group of people that interact, you get completely new phenomena, like Mexican wave or transport like this across the room. Electrons do also things like that, and that's what I'm going to tell you about most today. So, but we start at the beginnings. So, as you will remember, most of you will probably have learned that at high school. Quantum science started when the physicists realized that the space was mainly empty. There was a positive charge at the center of the atom and the electrons going around somewhere at a very big distance, and they had to make models to describe that. And so Bohr made the model where it is an orbital like that, a fixed orbital like the Earth going around the Sun. But the much more true way of representing it is what Born came up a few years later. You cannot actually describe exactly where the electron is. What you can do is describe the probability where you will find it in space if you do a measurement. So there are certain places in space where the probability that you find the electron is higher than in others, and this is the correct image. Schrödinger put all this into equations and described these spaces where the electron can be. So this is all the orbits that you can have for a hydrogen atom. And all these states are described what we call the quantum numbers. The first one is linked to the energy. The second one, you can call it linked to the angular momentum. Also, if you don't really can describe the movement, angular momentum loses a bit of the meaning. M is linked to the magnetic moment, and they are used to characterize the different orbits. And these orbits, they correspond to different energies. So we can define these states in which the electron can be around an atom. And the first ones were described like this. So all the states with n equals 1 have one energy. All the states with n equals 2 have another one, n equals 3. But this was calculated for the hydrogen, and hydrogen only has one electron. If you now add electrons, they also feel that the others are there, and instead of having only one state for every n quantum number, you get more states, and they have slightly different energies depending on the detailed quantum numbers that you have. And then what do you do if you want to know for one atom where the electrons are? Well, you put all the orbitals that you have, and you can fill them up with a maximum of 2 electrons, one with spin up and one with spin down. And so if you have the 1s, we only have one orbital, so we can put only 2 electrons. Then for the 2, we have the 2s, and we have the 2p. The 2p are actually 3 different orbitals, so we can accommodate a total of 6 here. And so we go on and also with the other levels. So then we can write the electronic configuration for sulfur, which has 16 electrons, is then the first one is fully filled, and so on. We don't need to go into detail. What I want you to remember is that there are different states for the electrons, and when it is in the ground state, that's the state where we arrive when we just fill every orbital with 2 electrons. Now, how do we know that all this is true? We know it because we can excite the electron from the ground state into a higher state, and that gives rise to the absorption spectrum. So if we send light with all the colors onto a gas, we see at the other side that certain frequencies are missing. Those are the ones which have been absorbed. And likewise, if we have excited the electrons and then we look what light comes out, we see that distinct lines come out. So that means we have distinct states into which we can excite or from which we can de-excite our electrons. So that was the beginning of the story. And when you know how to describe atoms, you can, of course, also describe molecules. You take an atomic level. Where's my point? Here. You take an atomic level from one atom and an atomic level from another atom. You combine them. You get, again, 2 levels, 2 orbitals. Yeah? Because you were starting with 2, you end up with 2. And then you start filling them, and you both can put them here because you only have 2 electrons. Likewise, if you continue and you have 4 atoms, you have these 4 states, you combine them, and you fill them, and so on. And you go on like this. And when you combine many atoms in a solid, what you see is that you always get the states above here, the states here, but now they are spaced much more tightly, and that is what we call then a band. So, if the distance is very big, we have the orbitals which we fill. This is now lithium. And then when we bring them closer and put them to the solid, we get, again, levels which we fill. So we have n lithium atoms, which means that we have n electrons on the last orbit, which means we have n orbitals, 2 n states, and this is how we do it. Nano-sized particles are somewhere here, between the isolated atoms and the large solid. So they are sort of molecules, and that's also how they behave. So we have distinct states, like for the molecules I showed you before. But the interesting thing is that depending how large the nanoparticle is, yeah, the distance between these states is different. So if we excite an electron that is here to here, we need a different energy than when we excite an electron from here to here. So if we make nanoparticles of the same material, the optical properties will be different. And that is the same thing we are going to talk about now, because this is something for which the Nobel Prize was given a few years ago. Quantum dots. Quantum dots are nothing else than a nanoparticle, in this case not of a metal, but of different combinations. And in order to stabilize, one puts molecules on the side. And then, depending how big this particle is, the fluorescence, the light that you get out, is at different wavelengths. And you can also see that by eye, because you see that they emit very different colors. And that is a very nice quantum phenomenon that we can use for practical applications. So, for example, we can inject this into tissue or even into living beings, and then we can see it light up under the microscope. So we can make it that these ligands attach to something particular in the tissue, and we can visualize that in an image. We can also use the fact that if we make the quantum dot of a certain size, it will emit a certain color. So we can make displays with screens with these quantum dots. We can also make solar cells with these quantum dots. I'm showing the one from the colleague at the University of Toronto. I could have shown the ones of Maria Loy here in Groningen, but I did not find a nice picture on the web. So I took the one of this colleague. It's not very spectacular. Anyway, the nice thing is that they work very well. Spectacular efficiencies, and in the future they will certainly become very, very important for solar cells. Right now, we want to make them better for the environment. So we don't want them with cadmium, we don't want them with lead. And Maria Loy's group is working very hard, and they have the first ones, but there are still issues with long-term stability under the light, heat, moisture. They are getting better every month, but we are not yet at the totally commercial level. So that was semiconductor, non-metallic quantum particles. What if we go to a metal? Well, for this I have to explain you what gives the color of a metal. And that is a bit different as process as what I told you before, because in a metal you have all the outer electrons, the very outer electrons of all the gold atoms, for example, they are all put together and they form a negatively charged electron gas, which is around the ionic cores of the center of the atoms. And what you can do then is that you apply an electric field and you move all this gas with respect to the ions back and forth. That is called a plasma oscillation. And you can excite that in the bulk, not with light, but on the surface. So the surface atoms, you can excite them that the electrons oscillate like this. And it's actually that energy which gives the color to gold. So the gold actually absorbs blue light, which means that the yellow light is reflected, and this is why the gold looks like that. Now the exciting thing is, I told you before, when we make things small, the distances between the levels change, and the same is true for these plasma oscillations. They change as well. So depending on how big I make my nanoparticle and what shape I give to the nanoparticle, it will have a different color. And you have all seen this. You just didn't know that you saw it. Because it is the glasses, the red of the glasses of the windows. It's also Roman glass who has that already. That is nothing else than gold or silver nanoparticles in the silica matrix. And because they are nanoparticles, the color is no longer yellow, but the color is red or blue or green, depending on the size and the shape of the nanoparticle. So making nice glasses is one thing, but there are also more exciting things that you can do. So, for example, Thomas Edison discovered that if you make very tiny holes, this is 2 micron. So this is like a hair, not even a hair, smaller than a hair. So if you make such tiny holes in a thin plate, you know, there is not much light which can go through. But he found that there is a lot of light which goes through. And that goes again via this surface plasmon. So the light which goes on this face of the plate excites the electrons. This travels through the holes and decays on the other side, and you get the light back out. So you can transmit a lot more light than you would think just from the surface of the holes to the other side. And this can be used because it works also with very tiny objects. And this is used, for example, for optical fibers. Normally, when you have a very small hole in the optical fiber, the intensity which comes out here is not very big. But the Japanese research group found out that if they put here a tiny little gold disc of 100 micron just in front of the hole, not covering, not attached to the hole, but just you can excite the surface plasmon, and you get a lot more light out in this way. So these are all tricks which are related to the properties of gold when it is very small. It's also useful for medicine. You can make these little cubes, and again, depending how thick, so these are hollow cubes, and depending how thick you make the walls, you get different colors, which are now these plasmon excitations which decay. And this is used a lot in transporting drugs, or in using the fact that they absorb near infrared radiation, so no longer in this visible part, but at lower wavelengths. Because these nanoparticles, they can go to cancer cells, and then we can do 2 things. Either we use the fact that we tune the size of the nanoparticle to absorb near infrared light, and when you absorb infrared light, it becomes hot. So if we put ligands on these particles that will only attach to a tumor cell, that is what one does. One directs these nanoparticles to the tumor cell, as you can see here in the image, and then one shines infrared light. Infrared light can go under the skin for quite a bit, so one can heat things up and really kill cells in this way. And this paper, for example, shows how this is done for, for a tumor in mice. You can also attach a ligand, which is like a brush on the outside of this nanoparticle, and you can have brushes which change with the acidity, and then you can put a drug inside, and when they come near to the tumor cell, the acidity is different, and they release the drug only there. So that is much better than swamping the whole body with chemotherapy. This directed way is much more benign to the patient. So these are other uses of the cell, but only the photothermal treatment really depends on the quantum properties. Something that you have all seen is another use. The red stripe that you saw in your COVID test is nothing else than these red gold nanoparticles, which attach through an antibody-antigen interactions on your test strip, and this is how you see them. Sorry, I have to drink a little bit. So these were round particles, or different shapes where the restriction was in all 3 dimensions. You can also make quantum wires, which are very, very thin wires. And you can make quantum wells, which is just one layer here in between, which is different from the other 2. And so the electrons which are here cannot escape to the other ones. They are confined to that plane. Now let's look for a moment at the quantum wire. If you take such a carbon nanotube, you have it on a conducting point attached, as you see here. Yeah, so this is 200 nanometers, so this thing is quite long and thin. And you go into a mercury bath. You can measure the current which flows, and therefore you can determine what is the conductance. Now, normally, conductance goes like water in a tube. The bigger the tube, the more the conductance is high. What you see here is something very different. When you go in, it doesn't matter how much you go in the beginning, you always get the same value. So it is really on-off as a measurement. And you see that the conductance goes up in steps. And sometimes you see a double step. This is when you have, like here, 2 nanotubes which are attached to one another. So when it comes to conductance, nanomaterials really behave different. And that is something that was actually already discovered here in Groningen by the group from Bart van Vaste during his PhD. What he did was he had a very, very thin conducting layer on which he made a constriction. So if the electrons want to go through, they have to go through this narrow constriction, which is called a quantum point contact. It is a narrow constriction between 2 wide electrically conducting regions. And how wide it has to be is what is, you know that we have the dualism between a particle and a wave. So if we look at the electron as a wave, it has a certain wavelength, and we have to make a constriction which is comparable in size to this wavelength. Then the electron really behaves in this way, and it behaves in a very strange way, because what you see is normally when you make this constriction broader and broader, if you had a classical material, you would just get a straight line. The wider is the opening, the more current goes through. This is not what happens when you have things at this quantum level, where the electron is very constricted. You see that you get these steps. And this is always the same number. It does not matter what this conducting layer is made of. Again, something completely different from normal material, where steel conducts much worse than copper, and so you don't get the same conductance for different materials. But here you do. So this is a very a clear demonstration that at the quantum level, the materials really behave very differently. But we still go weirder, and we go to quantum materials which are not tiny now, but they are extended materials. And they're essentially this field of looking at these phenomena. It started long ago, but it's getting more and more attention in the last little more than 10 years, where people look what are all the strange things that electrons can do, depending on the order of the atoms, depending on the topology. They can also be entangled, they can interact, and there can be dynamics. So before, I told you that in a metal, you have this strange situation that all the electrons of all the atoms of a metal, they make one electron C. And one way of seeing that is saying they are all entangled, they all communicate with each other. And in fact, if you change the place of two electrons in the solid, all the wave function changes. So all the electrons are affected by that, which is already quite amazing. You all know that when you have water at low temperature, it's ice. Then you heat it up, it becomes a liquid. When you heat more, it becomes a gas. So you have phase transitions, where you have the same stuff, but it behaves completely differently. Well, the same thing you can have with the electrons. And that is what Kamerlingh-Onnes discovered when he discovered superconductivity. So a non-superconductive metal, if the temperature goes down, then the resistance also goes down, more or less like this. But there are materials, aluminium, mercury, lead. If you go down with the temperature, all of a sudden, the resistance drops dramatically. And this is really a completely different state. And it does not happen for all metals. For example, gold is not superconducting. We have gone down to the lowest temperatures we can reach technically, and we have never found a superconducting state. So what shows that something is superconducting is when it expels a magnetic field, and this is how you get levitation. The way this is explained, that this state arises, is what you get is that an electron, when it travels through the crystal, it can deform the crystal locally. So it can displace atoms and sort of get dressed with this displacement of the atoms. And that makes it that another electron is attached and also gets dressed with this displacement. So the two electrons at this point are no longer repelling each other, but they are attached together. They have formed something new, which is these two electrons, which we call a Cooper pair, with this dressing around. So it's really something, a behavior which is completely different from what normal electrons do. And we have a lot of sorry, we have a lot of materials who do that. Here in blue you see all those who do it at normal pressure, and you have in green those which you have to put under high pressure to induce this superconducting state. So people thought they had understood this, but then they realized that there were materials that would show this behavior at much higher temperatures. And they had quite complicated compositions, and some you needed to apply a lot of pressure. But people started to see that it was not only with liquid helium. You could also get it with liquid nitrogen. And then the hope is, of course, to get it sometime at room temperature. But these new materials, the high temperature superconductors, they are very strange materials. And when I say very strange, they don't have only this phase transition to the superconducting state, they have lots of phase transitions to complicated states. So here you see, as a function of the composition, you put extra, you take electrons out by changing the composition a little bit. You have a certain part where the composition gives you a superconducting material. Then you have, if you go down, you get magnetic material, you get a strange metal. A strange metal is a metal with an unusually high resistance, much higher than normal metals. And that is because you don't have all the electrons which are entangled, which talk to each other in the same way, but you have local parts. So you have a sort of a Mexican wave. In certain parts, the people are excited, and in certain parts they are not. So they communicate differently in different parts of the solid. And then the stronger is the entanglement, the more you get the higher resistivity. So this is a strange metal. That is what you have up here. But here you have charge density. So the electrons sort of make a regular structure where you have more electrons, less electrons, more electrons, and so on. So really a strange distribution, which is no longer necessarily exactly the distribution of the atoms in the solid, but something that the electrons decide by themselves. So you see, it's something which we are starting to describe better and better. And what helped us a lot in describing that is that now we can make artificial solids, because we take just one layer. It started with graphene that you peel off with Scotch tape from the graphite, and you put it somewhere else. And the same we can now do with a lot of layered structures, and we make solids where we decide how we combine them. And from this we have understood more and more things about this, how they interact. The dream is to really understand this better in order to get to superconductivity at room temperature. Yeah, we are still 100 degrees down, more or less. Sometimes there are claims that we get closer, but it's still difficult because we don't really understand how it works yet. So what we will have then is much better magnetically levitated trains, because we will not have to cool to get the superconductivity. We will get better MRI machines where we don't need the cryogenics to cool down to have the superconductivity. Particle accelerators, right now we can make superconducting cables, of course, but there is always the liquid nitrogen that we need. So technically it's complicated. And the dream is also to have electronics where it's not a normal current, but it's a superconducting current that we can use, and that has a lot of advantages for ultra-fast circuits and logic gates, and will consume a lot less energy. So another thing I talked about was topology. I mentioned. What is topology? Is something It's a branch of mathematics where you describe how an object looks like while you are deforming it. So from the cup, which has a hole here, you can deform it to go to a donut. What you cannot do is make holes appear or make holes disappear. That is not allowed. But you can change things to go from one form to the other. And when a material has these properties, it also behaves in a little special way. One way where you have it is in what is called a topological insulator. A topological insulator is a solid that does not conduct electricity in the bulk, but conducts electricity at the surface. And what is even more special, the current with the electron spins in one direction goes in one way, and the one with the electron spin in the other direction goes in the other way. And you can do that on all surfaces. If you make a contact and you send in a current only of electrons with one spin direction, it will travel in this way. And the same thing you can do on in 2D on one layer. And that has been proven experimentally already that you can carry current without dissipation in these layers around the edges of this plane. So you can make a new type of transistor. A transistor is something which is off or which is on, where current flows or it doesn't flow. You can do this with these materials where you can apply an electric field and switch from a situation where there is no current to a situation where there is this current around the edges. And so there are quite a few people. Michael Führer was here a few months ago, and he gave a whole lecture at Zernike about how topological transistors could consume just half of the voltage, a quarter of the energy, and do the same function. So this is something where we are really going towards in the future. I think I will stop here for our break and tell you the rest afterwards. Okay, welcome back. And what I would like to tell you in this last part is to start again long time ago, 1911, 1919, magnetism. These two people, Niels Bohr and Johanna von Leeuwen, each wrote independently, not knowing of one another, wrote a PhD thesis, and both demonstrated exactly in the same way that magnetism is a quantum phenomenon. There is no classical theory with which you can explain it. And you will say, well, how is it possible? Johanna von Leeuwen was a PhD student of Lorentz. She's the fourth person, female person in the Netherlands to get a PhD in physics. And what you can see there is that there are the years of the First World War between the two, which completely blocked all communication. And also Lorentz was not at the Solvay conferences, at the two Solvay conferences before the First World War. And so he did not know about the ideas that were going around at the time about the explanation. Today we know it, and this is the thesis. But at the time, both of them only knew of the phenomenon that you could have materials that were attracted by the magnetic field and materials which are repelled by the magnetic field. And the ones which are repelled, so you can have levitation. That is the experiment of Andre Geim in Nijmegen. Water is one of those materials. So you can float a frog. And at the very high magnetic lab in Tallahassee, they have in the meantime floated mice. So but they knew about materials in which you could orient the magnetic moment with a magnetic field, and they knew about magnetic materials where all the magnetic moments were oriented in the same way. The antiferromagnet, where one is up and one is down, and so totally the material is not magnetic in the sense that you cannot attract iron with it, that was discovered only in 1930 at the time. And of course, in the meantime, also, there have been new developments. First, people discovered that they were very complicated magnetic phases. So this is one compound where you have here a phase where all the magnetic moments are like that. Another one where you have some which are up and some are in the plane, and so different orders all over depending on the temperature and on the magnetic field you apply. So again, we get different phases. It's very complicated. We understand a little bit more of those. But right now, in the last 2 years, people have been fighting a lot about altermagnets. What is an altermagnet? You see the ferromagnet, all the magnetic moments are in one direction. The antiferromagnet, it is up, down, up, down. I made a mistake here somewhere. It should be all up, down, all the way through. And the altermagnets, they go in this strange zigzag way. And so there are Maxime Mostawai of our university just published a paper describing how this works. So this is a really, really very hot topic at the moment. Now, why are magnets so important? Magnetic materials, because they have lots and lots of applications. We use them in data storage, we use them in sensors, we use them in all kinds of devices. So I just show you a few things for those who are maybe not so familiar. So you have in the windmills, you have permanent magnets which are attached to the rotor, so that gives a changing magnetic field which generates a current. This is how we use them. And these permanent magnets that we use for so many applications, also in loudspeakers, for example, as you see there, they are made of something which is a lot in the news these days, rare earth. So there is a lot of research which is not on the quantum properties, but how to make new materials which have these same magnetic properties and which we can replace. And there is a lot of research going on that. And I come to the last topic and the shortest one I'm going to tell you about. And that is also a very hot research at the moment, because in the last few years, you see the years of the publications, we have understood that a lot of these strange behaviors, we can induce them with light. So we don't need everywhere very cold temperatures or high pressures or things like that. We just need very intense light sources, which is not so practical at the moment because they are expensive too. But if we learn to make progress in this sense and how to go, this could open a lot of new ways. So instead of having only the temperature and a static parameter, which can be the pressure or the composition, which is what I showed you before when I discussed, for example, superconductivity, we have the light-matter coupling as a completely new parameter. And so far, it has been demonstrated that you can induce superconducting-like optical properties. The authors say it is superconductivity, but people are still fighting about it. We know that we can induce magnetism with light. We can induce ferroelectricity, which is moving something that there are electrical dipoles in the material that can also be done with light. So we don't need low temperatures for all this, but it always goes with the light that you need a very intense pulse. So it's not a permanent property, but you excite it and then it de-excites with time. So it's a very exciting field of research, but here we are still far from the applications. What I also want you to realize is that there is a lot of investment worldwide on this type of research. So the global effort in quantum science right now is 38 billion. So all the different nations are trying to do that, but this is not only on quantum materials, it is also on quantum communication. You will maybe remember the lecture by Zeilinger, who was talking about how you can use photons to transport information over large distances. It's also on quantum metrology, so very precise measurements on physical quantities, so atom clocks, things like that, and quantum sensing. So for example, this is something which is already applied and people use it in construction. So if you want to know, like now the ring around Groningen where you built, how is the terrain under the street? What you can do is you measure gravity locally and very precisely, and you can do that with quantum devices. And you know whether there are empty spaces or there is water, and you can make a whole map based on these gravity measurements. And that's something which is just one way of sensing, in this way, in this case of a gravitational field, but there are many other senses too. I won't talk about quantum computers because there is the Nobel Symposium next month, where you will learn about the physics which is below at the basis of quantum computers. Very, very simply speaking, what is the thing which makes these things possible? It is that you can, when you make these superconducting Cooper pairs, and they travel in the superconductor, and then you put a material which is not superconducting. You would think it gets blocked there. But no, the fantastic thing is that it can go through this wall and continue at the other side. And so you can make very special circuits with these materials, and that's what's in there. And just to tell you, I have been in San Sebastian 2 weeks ago, where they have one of the first quantum computers of IBM with 155 qubits. So that's very little, 155 is not a lot. And they interface it with a classical computer to do calculations, and things which would take a half a year of computing time, they do it in 15 minutes. So it's really impressive what is going to come with this technology. So that's all for today. I thank you very much for your attention.
Very much, Petra. You took us with very simple, seemingly simple steps through very complicated material. So I guess there are lots of questions in the audience. So who can I give the word first? If no one yet, there is one in the middle. And maybe I can already start asking you to elaborate a little bit on something you showed very early on in your presentation on the tumor uptake of these materials. Yes. It's intravenously injected.
Yes, exactly. But as I explained, on the nanoparticle, I show it big like that, but of course, you have these ligand molecules which are attached, and with which you can do a lot of tailoring. So you can attach something that will only go to a certain place, and you can attach things which can hold other materials, a medicine, or you can make it, you can use it for the optical properties. And right now, it's just by chance that this morning I submitted a paper which gives the last a review paper on the last developments in this field. Yeah. What people are trying to do up to now, a lot of these studies have been done in vitro, but there is very little in vivo yet. So there is a big movement now to understand exactly how these nanoparticles behave in order to go really to clinical applications. But it's going to come very soon.
Impressive. The microphone has landed to the question.
Thank you very much for the lecture. My question is, please, out of or looking from the photoelectrical effect by Einstein and others, and recently, but what about energy levels of the electrons in within crystal structures or atoms, and fluorescence you mentioned?
Yes.
When electrons descend in level, but the movement of one level to another, is that also controlled by photons?
Yes.
In practice?
Yeah. One example is the washing powder that you use. If the publicity says whiter than white, what you actually get is a material which is mixed with the washing powder, which does not wash at all, but which absorbs UV light and emits visible light. So your washing actually glows, only very little, but it has a real effect. When you see it, it looks whiter than white because of this effect. So that's a trick that the washing machine, the washing powder producers have been using for already decennia, which is a completely useless material, except for selling the washing powder. So
yeah, thank you for your very intriguing lecture. But in the beginning, you mentioned something about metals.
yes.
And the color characteristics in different environments. I'm highly intrigued by the changing of materials like cobalt or copper when they are taken up in glass substances.
Yes.
Can you say something more about these characteristics?
Yes. So actually, the way you make it, you start with the salt, and then it makes the reaction and makes the metal nanoparticles. Of course, the Romans or the medieval glass masters, they did not know how it worked. We know it now for some 20 years, when at the synchrotron people looked at these materials and actually found out what they were, because there was this intriguing question, what is the red glass? So, or the blue glass and so on. They are all these particles. So it can be made really low-tech manner, but the way we make it today is really is a bit more sophisticated because we want to tune. So we are not happy only that it is red, but we want that it is red with a very particular wavelength. So for example, if we want to use it for the photothermal therapy for cancer, it has to be at the low infrared side so that the light penetrates into the tissue. And all these things are much more controlled nowadays than at the time of the Romans or the medieval times. So yes.
Petra, I much enjoyed your very enthusiastic lecture. I was touched by your strange metal discussion.
Yeah.
That unusually high resistance by inhomogeneous electron distribution. Is that calculatable?
Yes.
That's my question. And can you arrange that?
People are working on it to make satisfactory models for it. But it is not the density of electrons. It is how much they interact. So in a normal metal, all the valence electrons interact in the same fashion throughout the crystal. In these strange metals, you have sort of hotspots where they interact more and other places where they interact normally. And that gives these strange metal properties.
And is that interaction dependable on where they are? So is that also a matter of distribution? Or is that just a matter of interaction? And is that, let's say, a higher level of interaction?
So we don't have a finite model for this yet. There are the first description of how that works. So we know that it is not the density of electrons, but it is really the modulation of their interaction. And that becomes more difficult to model. So
okay, thank you.
Okay. There are no further questions. It's hard for me to see, but I think then this is it. Petra will be around, so it's open for informal discussions. I also have many more questions, and I wonder why the tumor thing was not in your dreams. So let's see what we can do about that. We would like to give you a little present.
Thank you.
And since we thought you being so long a member of the board, you probably have the present we always give.
Yes.
So you better check at home. If not, then we have a copy for you. But George has been so kind to scratch his brain and see what would be, well, appropriate for our Petra, if I may say that. So he came up with the new book of Ian McEwan.
Oh, nice.
Ah,
Yes.
that's here. Very good pick. So this is entitled What Can We Know? And it's, you know already about it, so I'll tell the audience. It takes place in 2190, so very far away. It's a science fiction book, but without science. And it, I was informed, I didn't read it myself, it plays in the UK, which is underwater for half of it. So I don't know if it's very much fun to read, but it will probably enlighten you. So
Thank you.
Thank you very much.
Thank you very much.
So before inviting you all for the nazit, the after lecture drinks, I also very much like to invite you all for the Nobel Symposium, which is next month, already introduced by Petra. And also we have the Van Swinderen Symposium, which are yeah, kind of different from the normal lectures, which we will restart in January. But we do hope to see many of you also there. Both are in the evening, so normally the Nobel Symposium is in the afternoon. Make sure you mark your calendars right, that it's in the evening. So looking forward to see you there and at the drinks. Thank you all for being here. And thank you.